In this assignment, we will compute basic topographic parameters and landforms. Let me switch to the assignment 5 map set. And let's first define the region. We will be to get a closer look at the spatial pattern of slope and aspect and explore its properties. We will change the region to a smaller region than what we worked with before. And we will do it by moving our east coordinate 7 kilometers to the west and moving our southern coordinate of the spatial extent 7 kilometers to the north, using one of the options that is available in g.region command. So let's just copy. So first, we will set the region to raster elevation so that we get the 10-meter resolution and the full extent of the elevation dataset. And now we will shrink it 7 kilometers to zoom into a smaller, to define a smaller area. And then we will compute slope and aspect for this area. And as you can see, the maps don't show up. So what do we need to do? We need to zoom to computational region. So now we have that, now we are zoomed into the region that we have defined. And this is the aspect. And this is the slope map. So you can see the pattern of the highways that show in the slope map. So let's change the color of the aspect to colored aspect, similar as we have in the spline interpolation output, and as you have also, I think, in ArcGIS. We will then save these maps later on. So what we would like to explore now is the impact of changing the floating point elevation data to integer elevation data. That means that we will essentially lose the decimals, we will lose the decimeters and centimeters, and we will have whole meters in our DEM. The reason why we are looking at this issue is that sometimes you will find digital elevation model distributed with integer values. For example, NCDOT has distributed 20-foot digital elevation model for entire North Carolina as with integer values at 1 foot vertical precision. So let's create a elevation file that has integer values. The reason why this is done is so that it takes much less space. And let's compute slope and aspect for this for the DEM that has reduced vertical precision. Okay, so we don't see that elevation file, but we will see the slope and aspect. And within the slope map, you can already see some changes here. So when you will be describing what is going on, you may want to focus on this area. You can even zoom into it. And now let's look how in this area the slope looks like when it is derived from the map that has only integer values in meters. So you can see there are steps on the highway, so the highway is not smooth, and also this is a big shopping area, so it has a lot of parking lots. Those have slopes, those have flat areas, these wide areas, and the steeper slopes in between. So let's move back to the full extent, and you can see that there are a couple areas that have this pattern as well. You can zoom in, for example, into this area. Again, it will have a lot of differences between the floating point result and the integer result, and the result from the integer DEM. It is also helpful, in addition to zooming into these areas that have different slope output, it is also helpful to compare the histograms. So let's first create some maps from the slope and aspect that we have just computed for that comparison for your report. Oh, we have it here. Okay. So we will display the slope, add the legend, and let's just make it a little bit nicer. And you may want to add the scale bar as well. You can make it smaller to fit better. Let's see. Okay, and we can save this map for the report. Now let's display the slope derived from the integer map. So you can see here you have those areas that have uh, flat locations, flat areas combined with steeper slopes. So you can see the white is zero slope. And for your report, you can zoom into these areas to better illustrate what's going on, but this is fine as well. So we don't need to do a new legend because the values in the slope map are, the colors are assigned in the same way. And let's just save it. Now let's display the aspect map. So we can remove this legend and this legend here. And let's save it. And let's see whether we have changed the color here. No, we didn't. So let's just change the color. For this map as well. This is missing here. Mhm. And again, you can see that pattern of discontinuous aspect along with these flat areas where aspect is not defined in all of these locations. So let's just compare it. So we will have, again, it will be different. And this will be. Okay, so these are the maps for our report that compare the spatial pattern of slope and aspect derived from floating point and integer DEM. It is also helpful to look at the histograms. So let's now generate histograms for these maps. So this is how the histogram looks like for the floating point output. Now you can get rid of that orange square here. I think it's here. Let's see. So under map display, you can switch off the, I didn't switch it. Okay, so let's just keep it this way. And we can save this histogram. Let me just get rid of it this way. And let's look at the histogram for the integer values. And let's save this histogram. Similarly for aspect, for the continuous data, we get a continuous distribution. And let's save it. And for aspect derived from integer map, very, very big difference. So you can see the bias towards certain values in the aspect map. So big difference in how the aspect would look like when you use integer versus floating point map. So in your report, please then explain the difference in slope and aspect maps and also how it shows up in the histograms. So now what we will do, we will compute and explore the computation of slope along a road. So you may remember that in the lecture, we talked about the steepest slope of topography that is defined as a magnitude of gradient of the surface, and that in addition to the steepest slope, we also can compute slope in any direction, but this slope will be different from the, will be often different from the slope, from the steepest slope. So let's explore it. So let's first set the region to the extent of vector layer that shows the bus route. So we will do it here. We can zoom to that computational region. It will be slightly different. Again, a subset of our original region. Now we will convert the bus route vector line to raster representation. And you may remember we have done it already several times. And we have used, usually we have used an attribute. In this case, instead of attribute, we will use the direction of the line of that line. So you can think about it as an azimuth. It's just computed from the plus x axis. So here is the bus route along with its direction. So that's this file. So let's look at what the legend says. So so you can see that we have the values from 0 to 360 degrees. So for example, this greenish line has a direction around 270 degrees. This direction is 360 degrees. So these are direction angles of that route. And let's just save it. So now let's compute the steepest slope of the topography in this area. And we will also compute the aspect so that we know the direction in which this steepest slope points to. So we have slope and aspect map. So here is that slope map. And we will now extract the values of this slope map for our route. And this is our output. And let's remove this legend because this is the slope. This is the steepest slope derived from the digital elevation model around this route. Now what we want to do, we want to compute not the steepest slope, but the slope along the route. And this is a common task, for example, when you want to design a trail. You want to make sure that the trail is not too steep, for example, to ensure accessibility. Same for the road. There are rules how steep the road can be. So again, you want to know what the steepness of the route, let's say it's a planned route, will be where the road would be built. And there are many other applications where you want to know what the slope in a certain direction is. So let's compute it. And let's assign a special color table to both the slope derived from the digital elevation model, the steepest slope, and the slope in the direction of that route. So we have changed the color table so that we can see the differences better. It's blue, cyan, yellow, red color table, which is histogram equalized. And let's also display the contours for the context so that we know how it relates to topography. But I see I have it here one more time with better color. So let's look at the contours. Let's look at the route that has the steepest slope. Let's display its legend. So the slope here goes from almost zero to 18 degrees. So there are some locations where the slope is pretty steep along this road, and it's usually around the road where where there are some man-made features. So, and let's save this map. And now let's display the slope values along that road, like in the direction of that route. So we can see that it's much, much lower slope, way below 5 degrees. And that's what you would expect for the road. We don't really want any very steep slopes on the road. So we can save it. And we can confirm that this route has much lower slope by looking at them, comparing the univariate statistics. Sorry. Slope, we call it BEM. So the range is 18 degrees and mean is 3.6. And let's look at the one that is in direction of the bus route. So the mean is half of what is the steepest slope. So again, for your report, answer the question, what is the difference between the two slope maps and which slope is steeper? Again, very straightforward. So now let's look at the computation of curvatures. And we can compute curvatures using R slope aspect, and R slope aspect is using the 3 times 3 window and polynomial approximation to compute the second order derivatives, and then using the first and second order derivatives to compute the curvatures. So you can try out yourself how the slope and how the curvatures will look like when you use R slope aspect for this computational region. But I will show how to compute it as output of vserf RST of the spline interpolation. So we will have as input bare ground the LiDAR points, and we will compute the 1 meter resolution DEM along with profile curvature and tangential curvature. So let's just set the region to our small rural watershed. And we are not seeing anything, and the computational region boundary has disappeared, so that essentially tells us that we are not looking at our computational region. So let's zoom at it. Okay, so now we are looking at our computational region, and the curvature, not really that great. And what you can see from the pattern of this curvature, you can see these stripes here. And those stripes here are actually capturing the distribution of LiDAR points. So what can we do about it? So let's save it. Let's save this, the map of profile curvature. Again, you can see very, very noisy, very subtle, great detail. Not all of it is actually the topographic features, the curvature of topography. Rather, it is influenced by the interpolation that is biased towards the points. And we have already seen that before. So let's now save these maps for our report along with legends. So I will erase the the display and just display them again along with the legend. I can make the legend a little bit smaller. And let's just zoom to computational region. Okay, so this is the profile curvature with the default tangent, so we didn't change anything. Let's just save it. Let's now erase the map and display the tangential curvature. You can see slightly different pattern. This is the curvature along the contours. The profile curvature was the curvature along the flow line in the direction of gradient. So again, the legend will be very similar. I can keep it this way. And let's just save it. How can we now change the interpolation so that we get the less bias towards the pattern of the LiDAR data and more, and instead the curvatures that are more aligned with what we would perceive as topographic features or landforms? So what we can do, we can lower the tension. So you can see, you may remember that the default tension was 40. Here we are lowering the tension to 15 and increasing smoothing. So let's just redo this computation and again save the results. So we are computing, this is tangential curvature, and we are also computing profile curvature. And as you can see, these are much more reasonable results, much easier to read and interpret. So in the profile curvature, you can clearly see the pond. You can also see the road here, another road here, and the valley. The valley is very well represented in tangential curvature and all these other ones. So let's just save this as for our map. So let's just save the profile curvature. I will do them again just to make sure. You can see when you compare these values that with the lower tension, that the values of the curvature are much smaller than what we had with the higher tension. So it's almost the extreme, the minimum and maximum are almost the 1 magnitude lower. So this is the profile curvature. So let's save it. And then we have tangential curvature. Again, it really pulls out the road and it pulls out all the valleys. And how does our legend look like? Again, much smaller values than what we had in the surface with higher tension, and it now represents much better the curvatures in the topography rather than the curvatures that were artifacts of surface interpolated with tension too high. So let's save it. So here what you can also do, you can display these curvatures draped over digital elevation model. And for that, you would use this output. Do you see, like, we computed elevation, leveled 1 meter. You can add that to the layers, then switch off the curvatures and just use this elevation file and switch to three-dimensional view and use outputs of the curvature computation as a color for your three-dimensional DEM. Okay, so the last part will be computation of landforms. So with the curvatures, what we have just profile curvature, tangential curvature. You can see that they are related to the landforms, but they don't explicitly tell us that this is valley, this is a ridge, this is peak. So what we can do, we can then combine the slope aspect, these two types of curvatures, to derive the more geomorphologically relevant landforms. So here, make sure to actually read the manual pages so that you know what are the features and how they are computed using two different tools that are in GRASS for computation of and extraction of landforms. So we will just confirm our region, and we will compute the landforms using the command rparam scale. And what this does, it fits a spline function around a moving window, and that moving window is defined by this parameter size. So in the first case, we will essentially use the parameters derived from spline function, which was fitted to 9 times 9 moving window. And in the second one, we will increase the size of this window and look at how does it influence the size of the landforms that we are extracting. So this is the landforms that were extracted with the size parameter 9. And this would be with the size parameter 45. A little bit longer computation, and you can see that we are getting larger scale features. So let's just add the legend. Or let me just compute the entire set of maps again. Again, you don't need to follow this exactly. You already have the maps there, so you can just add the legend and save them. So this is the landforms that are computed with from the 9 grid cells, and you can see that how these landforms are classified. So the blue colors that we have here are not just channels, but essentially valleys, and the yellow ones are ridges and shoulders, and the rest is like ridge and peak. Yellow, we have ridge, so you can see that the road is showing up as ridge. Green is pass, and these reds are local peaks. So let's just save this map. And here is the same map with the larger scale features. And you can see some planar features along the transition between the valleys and the ridges. And to see how they are represented in the contour map, we add the contours to this output. Oops. And again, what you can do, what I have in the lecture, you can drape this as color map over the digital elevation model that was used as input, and that's this LF lid 1 meter resolution. So this was landforms that derived the slope aspect and curvatures using a spline approximation on moving window. There is also a very different way and pretty powerful way how to extract the landforms using so-called geomorphons. And please look at the lecture, read the manual page for geomorphons to understand how they are different from these landforms that are derived based on surface geometry. And again, you have here some parameters that you can tune that will control the size of the features that you are extracting. So with the first one, we have the distance equals 0 and search parameter equal 50, and I think it's 50 meters. And with this second one, we will extend the distance to 10 meters. So we get a slightly different pattern based on changing these parameters. So again, I will erase, include the contours, and include the legend. And you can see this legend is different. It includes more detailed, more detailed landforms. So you have, for example, distinguish or difference between shoulder and ridge, while in the previous one it was just one category. So more categories and greater detail, but also more complex pattern. So let's just save this one, and the one with changed parameter. And then please comment on how does the search parameter and the distance parameter, how they influence the result that you are getting. So this is all in terms of slope, aspect, curvatures, and landforms. Then there is an optional part which includes raster time series analysis. So feel free to explore it using this by downloading this NextHead time series and putting it as your map set here, and you just copy it using the file manager, and then make sure that when you are unzipping it, you don't create an extra directory. And again, it's fairly simple, and the results are quite interesting, similar to what I had in my lecture. And as I mentioned in the lecture, cut and fill volumes and in general computation of volumes is very important for many applications, and especially during natural disasters. So you may want to explore computation of volume here as well.